Now what we are going to do is one theorem proving work here. So what we could show is actually for any of these heuristics that we go through, we can show something called an approximation ratio. So we are not going to do for all the heuristics, we are going to do only for this one. So for the twice around the tree, we can say its approximation ratio is 2. So what I mean by approximation ratio? So what we found is some tour, right? Or for a given complete graph of this edge weights, we found the tour to be 31. Now, is this the optimal tour? Means, is this the minimum possible weight of a tour on this given complete graph? We don't know what is the optimal tour, right? So with just this 31 number, you may think I cannot say this is optimal or not. But what we can say is how close is this to the optimal, or what is the guarantee that how close is this to the optimal. So that's what is this approximation ratio. So we are going to say the weight of the tour found by this heuristic is going to be less than twice the weight of the optimal tour. So this number 2, the factor here is the approximation ratio. So that means this 31 is going to be less than 2 times the weight of the optimal tour. And from this actually you can say what is the minimum possible weight for the optimal tour, right? So like in this case, 31 is the weight of the tour that you found by the heuristic. Is going to be less than 2 times the weight of the optimal tour. So the weight of the optimal tour is going to be greater than 31 divided by 2, which is 15.5. So that means we can say the weight of the optimal tour should be at least 16. So that's the kind of an application of this theorem. So we are guaranteed that by this statement, the weight of the tour that we got from the heuristic 31 is going to be what? Not more than twice the weight of the optimal tour. Is that clear? So it's not that the weight of optimal tour is some 5 or 10 or something like that. The weight of the optimal tour is going to be 16 or above. That's what we can say from the weight that we found from the heuristic. Okay. So naturally then people will, whoever comes up with a design for a heuristic for any of these NP complete problems, will try to reduce this approximation ratio as close as possible to 1, right? Because ideally we would prefer the weight of the tour found by a heuristic for an NP complete problem to be equal to the weight of whatever we are trying to find, say in this case the tour, the optimal tour, right? So we would prefer this weight of the heuristic to the tour to be say less than say 1.5 times the weight of the optimal tour, or 1.2 times the weight of the optimal tour. So in those cases, then the weight of the optimal tour will be even closer to the weight of the tour found by the heuristic, right? So that's why as part of when you are doing any research on this topic, so you will focus on coming up with a heuristic for the NP complete problem you're working on, such a way its approximation ratio is lower than any of the other heuristics that people have developed for the same NP complete problem. So that's very kind of, for the same NP complete problem, you would have come across several heuristics in the literature. And each of them will have some approximation ratio 1.4, 1.39, 1.38. So people will try to reduce even by a factor of 0.01 and say that's an improvement compared to the other heuristics available so far. So that's how research is one direction of research in this area. Okay. All right. So if you're interested in graduate school, you can think about all those things. All right. So now what you're going to do is show that the approximation ratio for this heuristic is this factor of 2. Okay, so let us go through the proof now. So the proof is simply based on the 3 steps that we went through. All right, so let me I'm summarizing a step here as well as using that to build the proof. So the first step what we went through is to build a minimum spanning tree of the given complete graph. So let us use this notation, the weight of the minimum spanning tree be considered as the weight of the minimum spanning tree we just found. Now the second step, what we just did is we ran depth first search on the minimum spanning tree and obtained what is called the DFS walk, right? So once we got the minimum spanning tree, we ran depth first search on it and obtained this walk around the tree. So and we know, as I said at the time, that the weight of this walk is simply going to be twice the weight of this minimum spanning tree, because we are basically visiting each edge twice. So that is why the end of the second step, what we found as the weight of this minimum spanning tree based walk, I call as MST walk, is going to be twice the weight of the minimum spanning tree that we found from the first step. Okay. Now the third step, what we are literally doing is trying to reduce the weight of the walk and transform the walk to a 2. So, and as I said, we are applying the triangle inequality property there to skip the repeating vertices. So by doing or applying triangle inequality, I said we are only going to be reducing the weight of the walk further if possible, but we are not going to increase its weight. So the weight of this tour that we find from the heuristic is going to be less than or equal to the weight of this DFS walk, right, because of the triangle inequality property. So that's what I have shown here. At the end of the third step, the weight of the heuristic based tour that we come up with is going to be less than or equal to the weight of the minimum spanning tree based walk that we got from the second step. So these are the 3 steps. So now let us proceed further and do some little adjustment to derive the approximation ratio. Now one thing we know from fundamental is, so if you have a graph of say n vertices, and say complete graph of n vertices and with edge weights, now you could find a minimum spanning tree as we just found for that graph of n vertices, as well as find an optimal tour. We don't know an algorithm to find optimal tour, but it will exist. There will be some tour that will be an optimal tour of the minimum possible weight on that given graph, right? Now think about this. Both the spanning tree, minimum spanning tree, as well as the optimal tour are spread over the n vertices. But we can confidently claim that the weight of the minimum spanning tree will always be less than the weight of the optimal tour. Now why is this? You see, think about it. This is a tree. So in a graph of n vertices, you need to have only n minus 1 edges to be part of a minimum spanning tree. Whereas in a graph of n vertices, you need to have n edges to be part of a tour, so that even the optimal tour should have n edges. So if you go back to any of the examples we went through, so this is a graph of 6 edges that we worked on. So you need 6, this is a graph of 6 vertices that we worked on in the complete graph assigned to you. So that means you're going to have 6 edges in the tour. So a tour, an optimal tour, is going to have 6 edges, and a minimum spanning tree is going to have only 5 edges. So we are 1 edge less. So there's no way the weight of a minimum spanning tree will be greater than or even equal to the weight of the optimal tour, because then that is not really a minimum spanning tree. We could actually use the optimal tour, right? That's the spanning tree, but of course a tour has a cycle, we cannot call it tree. So in a graph, in any graph or in any weighted graph, you are guaranteed that the weight of a minimum spanning tree on that weighted graph is going to be always less than the weight of the optimal tour on that same graph. So that's the observation we are going to make use of here. Okay, so what we are going to do is this. Now substitute the result for MST walk. Okay, so for the minimum spanning tree walk, in the second step, we got this equation, right? It is twice the weight of the minimum spanning tree. So substitute that in the result of the third step. So the third step, we have the weight of the heuristic for base tour is less than or equal to the weight of the minimum spanning tree based walk because of triangle inequality. Now replace this walk with this minimum spanning tree weight. So that's going to be twice the weight of the minimum spanning tree weight, right? So that's what I'm doing here. So the weight of the heuristic 2 is less than or equal to, instead of the MST walk, it is twice the weight of the minimum spanning tree based on the second step. So now we know from our observation that the weight of a minimum spanning tree will always be less than the weight of an optimal tool. So all I'm going to now do is replace this weight of minimum spanning tree with this inequality, that it is going to be less than the weight of the optimal tool. So when you're going to replace this with this inequality, the equal sign will go away and it will be simply going to be less than twice the weight of the optimal tool. So that's what you have to be very careful. It's not even equal to, because the weight of the minimum spanning tree is going to be less than the weight of the optimal tool. So when you replace this with the 2, so you're going to remove the equal sign and say this the weight of the heuristic based 2 is less than twice the weight of the optimal 2. Okay, so that's what is the definition for approximation ratio. So you see, ratio means the weight of the tool based heuristic divided by the weight of the optimal 2. So that is the ratio, which is in this case 2. That's the approximation ratio. Okay, so as I said, using this ratio, approximation ratio, we can kind of find out what is the weight of the optimal tool. 1 second. Okay, 1 second. I'll be back in a couple of minutes. 1 second. Let me pass this. Okay, I'm back. Sorry for that. So we can, as I said earlier, we can use this ratio. So given that the approximation ratio for this heuristic is 2, once we find the tool weight, before you apply the two-change heuristic, because the two-change heuristic is something separate that we do on top of this heuristic. So by applying those three-step sequence of this heuristic, whatever the tool weight we end up with, in this case 31, is the weight of the heuristic based tool. So now we can say that's going to be less than twice the weight of the optimal tool. So 31 is less than twice the weight of the optimal tool. So from that, the weight of the optimal tool is going to be, can be said as greater than this weight 31 divided by 2. So that's what I'm showing here. So that's 15.5, and since we work with integers in this graph, we can say the weight of the optimal tour is at least 16, the next possible integer. Okay, so that is how you can apply this theorem. Alright, so let me just quickly repeat it. So from the first step, we find the minimum spanning tree. So let us say weight of the minimum spanning tree is what we found. And second step, we obtain walk by doing a depth first search on the tree. So I say the weight of the minimum spanning tree based walk is twice the weight of the minimum spanning tree, because we walk on each edge twice. Then from the third step of by applying triangle inequality, we obtain a tour of the heuristic, whose weight is going to be less than or equal to the weight of the minimum spanning tree based walk, because we are just going to reduce the weight by using triangle inequality. Now, from a simple observation, for any weighted graph of n vertices, the weight of the minimum spanning tree is always going to be less than the weight of an optimal tour on the same graph. So this is an optimal tree. Minimum spanning tree is a tree with the minimum weight. This is a tour with the minimum weight. So both have minimum weight, but since this is a tree, it's going to have only n minus 1 edges. And this is, since a tour, it's going to have n edges. So a tree of n minus 1 edges, a minimum spanning tree of n minus 1 edges, is going to always have a lower weight than minimum weight tour of n edges. So that's why we have this less than. So now we can say, just substitute the second step result for the third step. So the weight of the heuristic based tour is less than or equal to, instead of the weight of this walk, we can say it's twice the weight of the minimum spanning tree. And from our observation, the weight of a minimum spanning tree is going to be less than the weight of the optimal tour. So that's why the weight of the heuristic based tour is less than twice the weight of the optimal tour. Okay, so that is this theorem. So let me save this and we'll come back. Any questions?